Hello. Yeah, I'll start by thanking the organizers for this opportunity. So this is a work that we recently submitted and it's currently under review. It's a work done in collaboration with these people. So let's start the talk. Okay, so I'll remind people about the standard scenario of gravitational wave emission from compact binary coalescences. So basically, you have two compact objects; they are orbiting around each other under gravitational influence. And just like accelerating charges emit electromagnetic radiation, general relativity tells you that accelerating objects will emit gravitational radiation. Because of the emission of gravitational radiation, the orbital energy will become more and more negative, so the orbits will shrink, and at some point, the objects will spiral inward and coalesce, and the remnant of that coalescence will be lighter than the total mass that we started out with, and the energy difference is actually the total energy that ends up at the future null infinity as in the form of gravitational waves. So that's the standard picture of two objects orbiting each other and emitting gravitational waves. Now we talk about two specific objects, two neutron stars, and they are made up of some fluid, right? And if the fluid has viscosity, then there is one other effect that comes into play, which is the tidal dissipation. So one of the neutron stars exerts some tidal field on the other, and because of that tidal field, the other neutron star develops, let's say, a oblate-like shape. And if there are fluid layers inside that have non-zero viscosity, the fluid layers will rub against each other, and there will be dissipative loss of energy. This energy actually is drained from the orbit. So because of this phenomenon, actually the orbital energy will uh, become less and less in value faster. I mean, the orbital energy will lessen in value faster. So the orbit in spiral rate will be faster in that sense, and the objects will merge faster. And because of this, we can see the effect in the gravitational wave that we can measure from faraway detector in a faraway detector, because the inspiral rate now has changed because of this effect. Now, in a standard scenario, okay, so the deformation of the neutron star under this tidal field, uh, it can be because of adiabatic tides. Adiabatic tides are named so because these are tides that are roughly constant with respect to frequency, and if you decompose the entire inspiral process into two parts, which has an adiabatic uh, inspiral, which approximates that the energy loss is very slow, for example. So that gives you adiabatic tides, and also there are dynamical tides which are actually dependent on frequency, and these are the energy loss that goes into exciting different modes of the neutron stars. For example, the F mode. And the dissipation of energy that we just described is the dissipative tide. So these are the decaying modes of the stars, which are actually dissipative. I mean that energy cannot be gained back by the orbits. So that's what's called tidal heating in general. Now, for a general neutron star under standard model physics, this viscosity is very small, so we don't expect to get any measurable effect. But what we can imagine is that we don't actually know what's inside the core of a neutron star. So, for example, there can be strange matter. And in this slide, I'm showing one of the possible channels of strange matter, how strange matter can arise inside the core of a neutron star. So you have up quark and down quark, and one of the down quark changes flavor into a strange flavor, into a strange quark. And at the nucleon level, you have a neutron and proton going to a lambda hyperon. So hyperon is the strange particle. So if this is the case, if there are strange matter inside neutron stars, you expect the viscosity inside the bulk of the neutron star to be high enough so that the energy loss because of this tidal dissipation is measurable to some extent. So in this work, we actually modeled that. We created a neutron star model with this lambda hyperons inside their core, and we calculated how much this effect can cause, how much a difference this effect can cause in the gravitational waves that we measure, right? So this is the E dot visc is the viscous dissipation rate. So this is dE dt, the rate of change of energy because of this viscosity. This is the dissipative loss. And this is proportional to some quantity called gamma bulk, which has a dimension of frequency. So it actually quantifies the bulk viscous dissipation rate. With this E dot visc, we can write down the in spiral equation. So the loss of rate of loss of orbital energy, which is minus dE dV, dE dt, E is the orbital energy, is the total flux that goes to infinity plus the flux that is lost because of the tidal dissipation. Now, with this equation can be solved by parameterizing the waveform in terms of a parameter called V. V is a proxy for frequency. We can write down V as a function of frequency like this. Because it's not mentioned in the slide, I just wrote it down. So capital M is the total mass of the binary, F is the frequency of gravitational waves, and V can be quantified as pi mf to the power 1/3. So in terms of V, we can write down the frequency domain phase, which is the most important quantity in GW data analysis, because that's the thing that we can directly implement into frequency domain waveforms and make our comparison with the strain data that we receive. So solving, so we have E prime is dE dV, so there we just implement this E, and E dot is written here. So with this, we get the phase. Now, okay, in this plot, I'm showing as a function of V what gamma bulk looks like for different total masses of neutron stars. Now, if you look at the plots, as the total mass increases, the total it's called hyperon fraction, the fraction of the total hyperon mass to the total neutron star mass that increases, and that's why we have a higher gamma bulk in general. So the black squares actually denote the maxima of these curves, and similarly in the before I go into this plot, I have to say a few words. So the thing that we are considering, the phenomenon that we are considering is the viscous, tidal viscous dissipation inside the neutron star. So there is the energy loss inside the neutron star because of the tidal viscous dissipation. And there is another effect that this tidal field introduces, which is tidal deformability, which comes because in the first slide that we showed, because of this shape change, there is a quadrupolar contribution in the phase of the gravitational waves. It doesn't have anything to do with dissipation of energy, but a new quadrupole movement as a function of time that is introduced because of the shape change. So for neutron stars, this tidal deformability is very important because it does have measurable effects in the waveform, for example. And what we claim here is that this tidal dissipation can also have measurable effects if there are lambda hyperons in the core. So here we compare the phase change because of tidal deformation and tidal dissipation, and plot as a function of the mass of the neutron star when the tidal dissipation can be important compared to the tidal deformation. So the solid lines are tidal dissipation and the dashed lines are tidal deformability. If you see that as mass goes higher, the green line is a 2 solar mass neutron star. For a 2 solar mass neutron star, you see that the tidal dissipation is dominated compared to the tidal deformation. Whereas for a 1.6 solar mass neutron star, you see that tidal deformation has the dominating effect. So as the neutron star is more massive, this effect is more pronounced. And at around 2 solar mass, between 1.8 and 2 solar mass, we can have a measurable effect which can actually dominate over tidal deformation. Okay, so in this plot I show, for a real gravitational wave detector what can happen. So here these are called bias studies. So basically when you do parameter estimation, your waveform model has a lot of parameters. You estimate what the parameters can be given the data. Now, if we do not consider, as is not done for standard waveform models, this tidal dissipation is not taken into account in the waveform models. If that is so, then recovering standard parameters like lambda here, the lambda tilde is actually the tidal deformation parameter, which is always measured if a binary neutron star signal is received by the detectors. But we show here that the estimation of lambda can have a distinct bias because we did not take into account the dissipation effect. So Yeah, so this is the equation of state considered here. And the baseline model is Taylor F2, so it's a frequency domain model which is based on Taylor expansion, and we show as a function of total mass, as mass increases, we see that the bias is higher. And with dissipation considered, you get a lambda measurement of 80, whereas if you didn't take into consideration, you get something like 35, for example, in the most massive case. So ignoring this effect, the bottom line from this figure is that ignoring this effect can have a distinct signature in estimating the parameters, and it can give you wrong values of the parameters. Similarly, these are for different mass values given in different EOS equations of state. So I'll skip this one. And then as a whole, we model the entire phase. Like if you see that lambda has a distinct variation with respect to frequency or V, so we modeled the lambda and corresponding delta phi, which is the change in phase, as a function of frequency starting from a low to a high one, and we model them with a rational Pade approximant, so to speak. Yeah, and then here I am plotting the phase, the delta phi recovered from a study, and the spread denotes the error in recovery. Anyway, so okay, this is the summary. So basically, tidal dissipation can be measurable in binary neutron star if there are strange matter inside the core, which is very possible. There are theoretical propositions for it. And if we can measure them for high enough neutron star, for example, say 2 solar mass, and so since the phase evolution has a distinct feature, this can be a smoking gun signature for the presence of such strange matter inside neutron stars. Thank you.
Thank you, Shamano. Do you have any questions? Godwin.
So if I understood correctly, what you're saying is that in the core of the neutron stars where the temperature is high enough to form strange baryons, the tidal dissipation effects are enhanced due to this formation.
Right.
I mean, this is probably a very naive question, but why not charmed baryons? Why only strange baryons?
That I'm not sure. Charmed behavior. But people have shown that for strange baryons, this viscosity has a specific form. I don't know about whether charm baryons are considered. So,
Do you have other questions? Yeah.
okay.
I wanted to ask you one thing. I wanted to know how you were modeling your fluid. You told that the core of the study you are modeling it as a fluid, right?
Modeling as a
Fluid.
fluid.
Yeah. So I wanted to know how you're modeling that fluid actually.
Actually, the model has been there for some time. The modeling, the inside the core modeling, we didn't do. We just took the model and we estimated what the changes in gravitational phasing can be. So the model actually, here there are some processes. So this is as a function of temperature, and zeta is actually the real part of viscosity. The viscosity here will have real and imaginary parts. One part will decay and one part will have oscillatory features. And there are some processes inside the neutron stars. I am not very, I'm not an expert on the processes that goes inside the neutron stars. So yeah, so Suprovo was the one who works on neutron stars per se, and I built the model here and gravitational effects. But we can talk about it later. In details, I am not sure right now.
Thank you, Shamano, for the interesting talk.